Hello and welcome. For decades, the mantra in computing was smaller, faster, cheaper, driven by Moore's law, packing more transistors onto silicon chips. But we're hitting physical walls. Making transistors infinitely smaller isn't feasible anymore. So how does the semiconductor industry keep pushing the boundaries of performance? The answer lies, increasingly, not just on the chip, but around it, in something called advanced packaging. Packaging used to be simple, just a protective shell with connections. Now, it's a critical performance booster. Think of it less like a box, and more like a high-tech neighborhood, where different specialized components live and work closely together. Two key concepts are revolutionizing this neighborhood: heterogeneous integration and 3D stacking. Let's start with heterogeneous integration, or HI. Imagine building a complex device like a high-end computer processor. Traditionally, you'd try to cram everything: the main processing units, graphics, memory controllers, input/output, onto one giant piece of silicon, a monolithic system on chip or society. But this gets incredibly complex and expensive, and if one tiny part fails, the whole giant chip might be useless. HI takes a smarter, modular approach. You build smaller, specialized chips, called chiplets. Your super-fast logic gets built using the latest, fanciest silicon technology. Maybe your input/output functions can use older, cheaper tech. Then, you assemble these different chiplets together onto a common base, like an interposer, or directly using techniques like fan-out packaging. It's like building with specialized Lego bricks, instead of carving everything from one block. This improves manufacturing yields, optimizes cost and performance for each function, and even speeds up design time. Now, while HI often arranges chiplets side by side, 3D stacking goes vertical, literally stacking silicon dies on top of each other. How do they talk? Through tiny vertical tunnels, called through-silicon vias, or TSVs. Imagine drilling microscopic express elevators filled with conductive material right through the silicon floors. This creates super short connection paths between layers. Shorter paths mean faster signals, lower power consumption because signals don't travel as far, and incredibly high bandwidth, vital for things like stacking high bandwidth memory, or HBM, right on top of a processor. We're even seeing hybrid bonding, which allows direct copper connections without bumps, squeezing things even closer for better performance. It's all about packing more power into a smaller footprint. The real magic happens when you combine HI and 3D stacking. Picture a sophisticated system: high-performance CPU and AI chiplets sitting side by side on an interposer, with stacks of HBM memory chiplets right next to them, connected vertically with TSVs. Other chiplets handling power, or I/O, built on different processes, are also integrated onto that same platform. This combination allows engineers to build incredibly powerful and efficient systems specifically tailored for demanding tasks like AI, scientific computing, and next-generation mobile tech. Of course, it's not all easy. Packing so much power tightly creates heat that needs managing. Designing these complex multi-chip systems is tough, requiring new tools. Testing them is tricky. You need to ensure every single chiplet works perfectly before assembly. The supply chain gets more complex, managing parts from different sources. And developing industry standards, like UCIe for chiplet communication, is vital for the ecosystem to grow. Cost is also a factor, though the performance gains often justify it. But the path forward is clear. Expect more hybrid bonding, maybe new materials like glass for interposers, and even tighter integration, potentially merging electronics and photonics. Advanced packaging, powered by heterogeneous integration and 3D stacking, is truly shaping the future of computing. So the next time you hear about a breakthrough processor, remember that the innovation might not just be in the transistors themselves, but in the clever ways they're packaged and interconnected. That's all for today. Thanks for tuning in.